Yeah, so I purposely kind of provocatively named my title because heavy ion physics is a kind of really interesting area of particle physics where we go sort of very close to the standard model, of course, but also there's a lot of kind of astrophysical implications as well. And I'll sort of talk about that in this lecture. So let's just get started. So kind of the base that I like to start with is kind of trying to understand how things interact, right? And so in the terms of chemistry, what we've understood is that if we want to understand how certain chemical compositions work or some kind of reactions occur, we need to understand how those constituents interact amongst themselves. So in this case, in chemistry, those are the atoms, right? An atom is kind of in two parts. There's the nucleus, right? This is this red and green section here. And then you've also got the negatively charged electrons. And the kinds of nuclei you have and the kinds of electrons and what energies, all of those kind of details will then propagate into what kinds of chemicals and what chemical reactions you can have. You can then go like zoom in a little further, and then you can ask, well, what is actually inside the nucleus? We used to think that the nucleus was sort of just like one big blob, but we've now understood that it's a little more complicated than that. It's made of both neutrons, which are neutrally charged, and protons, which are positively charged. You can go even more deeply than that and then start to look at, well, the protons and neutrons themselves. And it turns out if you look even deeper into a proton, you kind of see four different kinds of things. You see three quarks. Here we call them the up and down quarks, the U, and D. And then in between them, holding them together are these particles called gluons. And that's true for also neutrons as well. But in neutrons, the composition is a little different. Here we have just one up quark and two down quarks. And so that kind of gives us a different charge, and a lot of the different kind of behaviors that we understand to be different between protons and neutrons are due to this different composition in the same way that we think about chemistry. So the way we think about, or the framework that we have to understand how quarks and gluons interact, is what's called the standard model. So this is something that we've talked about, I think, in previous lectures also. So the way that the standard model works is essentially takes different kinds of particles, that a set of particles, a set of interactions that occur between those particles, and then you have some sort of framework that tells you, well, how can these interactions actually occur? And so there's kind of three main parts. There is the kind of green part, which is electromagnetism. So these are the charged particles. And here we talk about, positively and negative charged particles interacting with the photon. We also have the weak interaction, which is this kind of red section. So this is the area where we think about the W and the Z bosons. And then we have the strong interaction, which is this purple section. I should say you shouldn't read too much into the coloring, right? For example, the top is really actually more closely related to the weak and electromagnetic interactions than it is to the strong interaction. And of course, the gluons and photons are not really related to as much related to the weak interaction, but it's kind of like a good sense of how you can think about kind of dividing up this diagram of particles. The part that we want to focus on today is what's called quantum chromodynamics. So that's this section. It's the purple section where we've thought about the different quarks going from the up and down quark, which are quite light at 2 and 4 MeV. You go up by a factor of 50, and then that's the strange quark. You go a little heavier than that, about a factor of 10, you get the charm, and then the bottom and top are much heavier also. And then the gluons that kind of go in between. And so in the same way that the electromagnetism, you think about the charge as being the relevant property about what things interact and what things don't. The property here is what we call color. So it means that all of these kinds of particles, all the quarks and as well as the gluons, they can come in different colors. And so these we call red, green, and blue. And also the anti-red, anti-green, and anti-blue. So that's 6 colors total. And we understand that the bound states that we see, like the protons and the neutrons and so on, all of these objects are colorless, meaning that there's always some combination of red, green, and blue, or of red and anti-red that also gives you a colorless combination. And we use the term partons to sort of as a kind of generic term to talk about both quarks and gluons, and we'll talk about that. Those will come up much more in later sections. So what are we actually trying to learn about with quantum chromodynamics? You can take sort of a particle physics approach, which is to say, well, I have some sort of framework. I want to make sure that framework actually describes what I see in nature. So one question you might think about in the particle physics context might be, is quantum chromodynamics correct? Right? There's no reason that nature has to necessarily agree with you on what you think that nature should be doing, what nature's actually doing. So one way to do this is to do something very simple. You just do some sort of experiment. You have, you measure some property or some quantity, and then you ask quantum chromodynamics, well, what should I actually measure as that property? And then you can say, well, let's actually compare those things and see if they match. And that works in particle physics if those predictions can actually be made. But the problem is that in QCD, it's actually quite difficult. A lot of the kind of tools that you have, especially in these quantum field theories, like Feynman diagrams and perturbative expansions, which are essentially just Taylor series on steroids, really don't work very well in QCD for a variety of reasons. And so that means that you have to be really careful about what things you want to measure and what kind of conclusions you make about QCD. And so being able to compare these things to quote unquote standard model predictions are actually quite rare. I should say there's one exception. This is called lattice QCD. This is kind of our best kind of attempt at getting standard model predictions. It's not like a one size fits all hammer. It's kind of works only in very particular situations, but we are improving a lot on that front. So really what we want to understand with QCD is less about figuring out if QCD is correct and more about asking, like, what is QCD actually trying to tell us? What are the sort of general principles that we should understand both qualitatively and quantitatively about how these partons, these quarks and gluons interact? And on the flip side, you want to understand, well, what are actually the kinds of things we can measure in an experiment that actually tells us about those kinds of properties? So how can you actually study quarks and gluons? Well, I told you that the quarks and gluons are confined within hadrons, like these protons and neutrons, and that's because of a property called confinement. Confinement essentially means that at low energies, the coupling, the interaction between these kinds of particles gets really, really strong. That means that if you try to take a quark out, the system is going to really oppose as much as possible taking that quark out. And so that means that all the things that you see are going to be really bound states. You're not going to really see these quarks and gluons on their own. Now, if you want to actually understand how these things interact, it may be useful to actually get them out. And the way to do that is just in the same way that we'd actually, heat up a lot of different things and just to inject a lot of energy into the system. You can sort of think about, for example, the transition from going from a solid to a liquid to a gas. Right? In those cases, what you're doing is you're breaking down the chemical bonds that keep these things together. And if you just keep going beyond that limit, you keep adding energy, you might even go to what's called a plasma state, where the bonds that hold the electrons to the nuclei, they break apart, and so you get free electrons and free nuclei. And then if you heat it up even further, the bonds that keep these nuclei together will break apart, and you'll get protons and neutrons that are free. And then you go up even higher, and then you get what's called a quark-gluon plasma, where even the quarks and the gluons have now been freed, and now you can actually look at them and see how they interact directly. So that's the area of what we call heavy ion physics. And in kind of a one word or one phrase scenario, we might just say it's the study of many body high temperature QCD. If you had any, experience with statistical mechanics, this kind of really famous quote by Anderson, which is many is different. And that's really also very much true in QCD as well. Kind of the two body interactions that we might understand for like two quarks interacting, a quark and a gluon interacting. There are some things we can discern from that, but the kind of properties of the bulk of lots and lots of quarks and gluons interacting together is much different than if you just thought about two kind of particles looking at that. That's only one way about learning about QCD. There's a lot of different variables, a lot of different ways you can learn about QCD. I've given you just a short list of some others like nuclear structure, production of heavy nuclei and nuclear fusion. Cosmic ray experiments is also one. Lattice QCD, as I've mentioned, as from a more theoretical tool. Fusion and fission energy, of course, that's very relevant for nuclear physics. And of course, neutron stars and stellar fusion, and actually talk about neutron stars on a later point. So how can we actually collide heavy ions together? The facility that I'll talk about today, most likely for most of it, is going to be the Large Hadron Collider. This is called the LHC. It's on the border between France and Switzerland. It's kind of this large ring where you can collide all kinds of different particles. And so there are kind of four main experiments and a suite of smaller experiments that exist at the LHC. Today I'll be talking about the main four, which are ALICE, which is here at point 2 on the border of France and Switzerland. Also Atlas, which is near the main CERN site, and of course LHCb and CMS. And so all of these experiments have made a very interesting contributions toward this field. So I'll kind of try to evenly talk about all of them. So how do you actually create a quark-gluon plasma, right? It's not so easy to just kind of inject heat into the system over and over again. And the way that we do that is we actually can smash heavy nuclei together. So you may have heard at the LHC, we typically collide protons on protons. And so, for example, the discovery of the Higgs boson was made that way. But if actually for about a month to a month and a half at the end of every data taking year in about November and December, we actually also collide lead nuclei together. And the reason why we collide lead nuclei is because if we collide a large enough nucleus together onto another nucleus, what will happen is that you'll get so much energy that's deposited into a really small volume, and that it'll actually melt down the protons and neutrons that were in that nucleus. And so in that sense, you can actually produce a smaller droplet of what's called a QGP, a quark-gluon plasma, where these quarks and gluons are free to move around and aren't confined into a bound state. And this is called deconfinement. The QGP is very, very short-lived. It's only on the level of what's called a yoctosecond, or a 10 to the minus 23 seconds. So it's very, very short-lived. So it's not like we can just produce this thing in the laboratory and then go out, get a coffee, come back, look at it and be like, oh, I've made a QGP. You can't really say that. It doesn't last long enough to do that. So we need to understand how we can actually, identify a QGP and figure out its properties. And so the QGP itself will expand and it'll flow. It's kind of not a static thing. It'll expand because it's very hot. It'll expand into the vacuum around it. It'll then cool, and then it'll condense back into the hadrons, or these kind of composite particles that we see in our particle detector. And from measuring those kinds of properties, we can then connect that back to properties of the QGP. So one thing that's really, I think, a really interesting academic exercise is actually to think about, well, how do we know if we can't just look at it and see the QGP? How do we actually know that we've even produced the QGP? And this was actually a main source of concern actually in the early 2000s, late 1990s, when we weren't actually sure so much that, colliding nuclei would actually give us a QGP at all. So there are a couple of different ways we can measurements that we can do that actually can tell us whether we've actually created QGP. I'll talk about three of these: so strangeness enhancement, anisotropic flow or elliptic flow, and jet quenching. And those are the kind of three phenomena that I'll try to explain to you guys. And there are a couple of others. So a couple of others that I'm skipping. So for example, coconium suppression and the ridge structure. Those are other things that you can also look at. And essentially all of these have been satisfied in the lead-lead collisions that we see at the LHC. And so we're pretty sure that we are creating a QGP. And now we can move on to actually figuring out what kind of properties we can discern. So let's talk about the first one, strangeness enhancement. So we've created a kind of very dense and very hot medium. And so if you think about the mass of the strange quark, which is around 95 MeV, the temperature or the actual system size is around 300 MeV for the quark-gluon plasma that we can create. So that means that if we relate the mass of something to its energy using Einstein's equation E equals mc squared, that means that we actually have enough energy within this kind of quark-gluon soup to actually produce strange quarks out of not necessarily the vacuum, but out of this medium. Because, of course, the temperature of the system is much larger than the mass of the strange quark. So we actually can produce that. So that means that if we actually start measuring, if we can actually identify and measure the number, essentially just counting exercise of the number of particles that contain strange quarks, then we should see, in principle, a lot more strange quark containing particles, composite particles, than we do without a QGP. And so this is, for example, just one measurement done in 2014 from the ELISE collaboration, comparison to a couple of different experiments. And you can see the ratio of particles can actually go up to a factor of 10 relative to proton-proton collisions. That's telling us we're producing an immense amount of strange quarks from the medium that isn't just coming from the collision itself. Before we move on to the next topic, well, let me just do a quick aside onto something called centrality. And so this essentially is the idea that a collision of two lead ions, not all collisions are created equal, right? These things have, 3D structure. They're kind of big, right? They're not just kind of point particles. They have like actual size. And so collisions can actually look different collision to collision. And so one way to understand that is to think about something called centrality. And centrality essentially just quantifies how much overlap there are between two collisions, right? You can think about what's called a central collision, in which case if from this view, this is the kind of view as if you're looking down in the direction of the particle's motion, kind of down the particle trajectory. And here that means that if it's highly central, that means that there's the collisions are essentially head-on. Right? There's essentially a full overlap between the cross-section of one lead ion and the collision of another lead ion. Then these things can become a little less central and what's called more peripheral. And here this becomes more sidelong, right? So you don't get a fully head-on collision in this case. You have some sort of overlap, but there's also some parts of these lead ions that are just essentially passing by each other. They're not really interacting. We call them spectators, and you can actually see those from this view. Then they can become even more sidelong. Then we call them kind of semi-peripheral, and then at the most sidelong, we will call them peripheral collisions. And so centrality is a way for us to identify sort of how much overlap there is between these particles as they overlap. Now, why is that important? Well, if you think about the overlap region as being the area where all of these interactions are happening, that means that if you have more overlap, you should have a more large QGP volume, or you should have a larger medium overall. And that means that because there's more energy in that volume overall, in total, then it means that you should be able to produce more particles. And it also means that you actually fix the initial geometry of the system, right? In a central collision, if you sort of think about the overlap region as being the cross-section of the QGP, it's roughly circular/spherical, right? It's kind of got a kind of roughly circular shape. But as you go to more peripheral collisions over and over, you get something that looks less like a circle and more like an ellipse, right? So you've got kind of interesting phenomena that happen there, and we'll talk about that in just a minute. So we can also ask about, well, how does the QGP actually move? Right? We know it expands, but we know that it probably does not expand in all directions in the same way, because we know about this idea of centrality. Because if it's more circular, or more elliptical, that means that the gradient of the pressure in multivariable calculus terms is actually greater along the short axis than it is on the long. So if you think about this kind of cross section for this example of a sort of semi-central collision, you understand that the pressure in the center is quite large, but of course the pressure on the edge, because it's the vacuum outside, is very small. That means that the pressure decreases a lot faster to go from the center to the edge this way along the short axis than it does along the long axis. That means that the pressure, the force that's being pushed out in this medium, is larger along the short axis than it is along the long. And that means that if you should actually then calculate the number of particles, you essentially just do a counting exercise of just seeing how many particles you see that are emitted along the short axis versus along the long axis. The greater pressure should allow you to see actually more particles along the short axis relative to the long. And so this is what we call the anisotropic flow coefficient, or the elliptic flow. Essentially, you just do a measurement of the number of particles with respect to the angle. And so here at the 0 would be kind of along this short axis. Here 0 and plus or minus pi. And of course, at the along the low axis, which is at plus or minus pi over 2, we should see fewer particles. And so you can actually fit this distribution to a sine function. Then you say, well, okay, the amount of flow that we should see, the amount of anisotropy, is actually quantified in this coefficient in front called the V2. That means that if there's a large kind of modulation between the long axis and the short axis, we should see quite a large sine function, which should result in a large V2, and the other way around. So we can also think about centrality as a function of that. And so that means that if the more asymmetrical the system is when it starts out, we should see a larger V2. Meaning that in more central collisions, we should see essentially no V2 at all, and that's actually what we observe. Let's talk about the last signature, which is called jet quenching. This is my favorite because I actually work in jet physics. And so the idea is, well, we can understand the QGP sort of as a bulk. That's one way to do it. But also another way to do it is to understand is just to shoot something through it and so see, well, okay, how does the thing that I shoot actually get modified by the material inside? So this is something that we've been doing a lot. So for example, the Rutherford scattering experiment that told us that nuclei have some sort of structure on the inside. That was also a scattering experiment. And so one way we can do this is to use a large high energy parton that kind of punches right through the QGP and see how that gets modified. The parton itself, as it propagates through, because of reasons for confinement, actually turns into a spray of hadrons. And so you can actually see kind of signatures of a jet. I don't know where my mouse went. Signatures of a jet sort of in this example, where you see a large deposition of energy in sort of a small area in your detector. And this we call what's called a jet. Now, if you shoot anything through any other medium, you should expect that it should lose some energy, right? If you shoot, for example, shoot a bullet through some sort of material like an iron block, at some point, it's going to be losing energy as it passes through the medium. That means that if I measure a jet, I should expect that it should also lose energy through the medium. And so if I were to just do, again, another counting exercise where I count the number of jets that you see in proton-proton collisions as a function of the jet energy, by factor of how these collisions work, you should see jet energies that are quite lots of jets that occur at larger energies, and then a lower number of jets that occur at smaller, or fewer number of jets that occur at larger energies. If our theory about how this works is correct, that these jets lose energy, that means my curve should essentially just shift to the left. Any jets that are at this energy, for example, should get pulled over here because their jet energy has been reduced. That means that now what I can do is I can take these two spectra and divide them and produce what's called the nuclear modification factor, RAA. A is just kind of a generic term that we use for any nuclei. So in this case, it would be R, lead, you might want to call it. And so where we divide the number of jets in AA collisions and by PP collisions. And if you think about these two curves, if I were to divide them, I should get an RAA, a ratio of these two curves that's less than 1. And if it were equal to 1, then that would tell me, okay, I have actually seen no jet quenching at all. These spectra look essentially identical. So if I take the ratio of two identical functions, I should just get 1 as a function of the jet energy. And so here's one measurement from the Atlas experiment as a function of the centrality. We can actually understand, and this is the value of RAA. You'll notice that the value up here is 1 and the value down here is 0.5. And it seems that for all centralities, we observe a significant jet quenching amount of a factor of nearly a factor of half. So we can also think about, well, why does this centrality dependence also make sense? And that also does make sense, right? If you have a jet that's produced, inside a central collision, it's got a lot of QGP to pass through. So the amount of energy that it loses should also be a lot, which means that the ROA should be smaller than in a more peripheral collision where you have less QGP to pass through. And, at the most peripheral collisions, maybe at even 90 to 100% centrality, then you should actually see very little modification. Because again, the QGP isn't really doing much there, right? There's not much to pass through. Let's take a little closer look at actually this event display, and let's see what else we can determine. And you might ask, well, funnily enough, because of energies of reasons of energy conservation, you should actually expect that two jets should be produced predominantly back to back with the same energy, right? Because we are working in the center of mass system, so these energies should be pretty equal. But you'll notice that actually it seems that in this particular collision, that's not actually true, right? You've got a one that's, which I understand maybe is too small to see here, is around 205 GeV. And you've got another jet on the back-to-back region that is at 70 GeV. That means that somehow one jet has come out of the QGP with 3 times the energy of the other jet. So that's kind of weird to think about. Well, if they're both passing through QGP, shouldn't they both be quenched? And that's true, but you do also have to think about, it's not just the fact that the QGP exists at all, is that what also it should depend is how much of the QGP you're passing through, right? So in this particular case, let's think about just a very central collision. In this case, and let's say that the jet is produced, these partons are produced kind of in the middle of this kind of overlap region. That means that if they're going back to back, they're basically passing through the same amount of QGP roughly, which means that the energy loss that each of them expect should be also quite equal. But if you were to produce the jets not in the middle, but sort of near the edge, then that means that this red jet passes through a lot less QGP than the yellow one does. And so the yellow one, because it's passing through more material, should lose more energy than the red one. In the case of a more peripheral collision now, that means that because the overall QGP volume is actually it's much smaller than in the central version, you should actually observe maybe a less of an imbalance in the amount of quenching of one jet relative to another, because really there's very little room for this kind of asymmetry to occur. So this is one way of actually quantifying this. We can think about what's called the dijet momentum balance, which we call XJ, where we take the two highest jets in whatever collision we find, and we take the ratio of the lower energy jet to the higher energy jet. If all jets were quenched equally, regardless of where they were produced, we should see an XJ distribution where it was peaked essentially at 1. Because again, those two jets are essentially have the same energy after they interact with the QGP. But what we can see is actually, pretty obviously, as you go from most central collisions, actually the most probable value of XJ is not actually 1, but it's actually around 0.6. That actually tells us that it's actually quite likely in these central collisions, as we sort of understood from this sort of pictorial representation, that some jets should be more quenched than others. And as we go to the more peripheral collisions, as we go up in these colors from red, green, blue, purple, and then this gold, which is the PP reference, we actually see that the amount of symmetric energy loss goes up. That's telling us that actually the level of asymmetry goes down as we see this more peripheral, as we see these more peripheral collisions, and therefore the asymmetry in this energy loss goes down. This is telling us that not only is it important how much QGP you're passing through, but actually the length of the QGP that you pass through it all is also a very relevant, something that's very relevant in understanding how much energy is lost to this medium. You can even have like a very extreme example, which is something like this. This is actually a very early, this is from 2010. So actually the very first time that the LHC collided light ions. This is one example from Atlas, where they actually see a really extreme example of asymmetric jet quenching, where one jet is clearly, the one jet you can see here and here is very clearly not very much quenched at all, but the other jet essentially has kind of disappeared. It sort of kind of disappeared into this background medium. I mean, it's really hard to even distinguish where that jet has occurred. So even kind of these extreme cases can happen. Now, one assumption that I've made in this entire presentation that maybe you've caught on, maybe you haven't, is that we kind of assume that in proton collisions, we haven't gotten enough energy in a small enough volume to actually produce a QGP. And you might think that actually, okay, maybe that's a good assumption to make. And actually, for a long time, we thought that was true. And it turns out that it's actually really good to actually do all your dot your I's and cross your T's, because if you actually check, a lot of these signatures that we saw in lead-lead collisions that told us that we're actually producing a QGP actually do appear also in proton-proton collisions. And so this really calls into question sort of the things that we thought about. Well, what actually is the requirements for a QGP to be produced, and what kinds of effects are relevant in observing these kinds of observing these kinds of phenomena. So this is one, for example, of elliptic flow. You can see that this is all proton-proton data. You can see that the coefficient of V2 is not 0, right? It's a little small, 0.05, but it's still clearly, very inconsistent from 0. So we know that there's clearly some flow there. Another thing that I did not actually talk about today, which is called the ridge. This is something that you'd expect to find in a flowing collective medium, and that's actually like this small ridge shape you sort of see at where delta phi is equal to 0, but at large delta eta. These kinds of correlations only occur with large collective with a collective phenomenon, and of course also strangeness enhancement. You can sort of see as a function of the multiplicity, which is a one way of measuring the centrality. Actually, you can see that in proton-proton collisions, you can sort of see this increase in the strangeness enhancement. So a lot of these kinds of signatures we sort of do also see in proton-proton collisions. The one thing that we do not see, so you might be tempted to say, well, maybe then we actually are producing QGP in these proton-proton collisions. But the one signature we do not see, and that's quite interesting, is actually jet quenching. So in jet quenching, if we do a measurement of exactly the same thing as we were saying before, this RAA, nuclear modification factor, we take a ratio, we actually find that it is very consistent with 1. So it's kind of an open question. Well, we see all of these other signatures, but we clearly don't see jet quenching. So maybe something's happening here that warrants further investigation. Let's now also talk about the role of mass in terms of the flow of the QGP. So we can also think about kind of heavier quarks like the charm and beauty quarks and see, well, how do those partons, as they propagate through the medium, how do those things get affected by the QGP as it moves around? One way to think about it is, well, let's just apply all of our other observables, all of these other measurements that we did on top of this one, on top of these kinds of particles, and see what happens. So for example, we could ask, well, does it flow? The answer is actually yes. So this is one measurement of the flow coefficient, this V2. Again, my mouse disappeared. The function of this V2 is a function of the essentially the energy of the particle. And you can see that for essentially all of these, the charm flow coefficient is clearly non-zero as you go, and the beauty coefficient also is non-zero. And clearly, it also tells us that the beauty flows less than the charm, and that makes sense, right? If you think about kind of a physical picture, that's I think quite useful is to think about just a flowing river. If I dropped a leaf into it, that leaf will essentially very quickly flow with the same velocity and the same kind of speed as the river itself. But if I were to drop a rock in there, the rock, depending on its mass, it may kind of roll a bit, but doesn't go as fast as the river is. Or if it's a really heavy rock, it'll just sit there. It won't even move at all, right? So this is a question of, well, if I have some flowing medium around it, the things that are lighter, like these charm and pions, for example, which are on these black plus symbols, those should actually flow quite well, and we should see the most flow for those ones. And as you go up in mass and you progress from the leaf kind of example to the rock kind of example, then we should see less and less flow because it's more massive and it's harder to make them flow. And that's actually what we see here, and that's what we call the mass hierarchy. You might also imagine that we've been talking a lot about this kind of centrality, and you might imagine that if we had two collisions that happen, and the whole point is that they should collide. We want them to collide. We want all this energy deposition to happen. But you might imagine then on the flip side that if these two ions just totally miss each other, they don't even interact. They just there's no overlap. You go from kind of peripheral to what's called an ultra peripheral collision. Then these are kind of useless events. They're not really useful to us. And in fact, that's not true. There is no QGP produced. That's a fair fact. But you have to also remember that these lead ions are very, very positively charged. We've taken all the electrons off of these atoms, so they're intensely positively charged. That means that the electric field around them is incredibly dense and incredibly energetic. That means that even though your actual ions may not be colliding, the electric fields, or essentially the photons that are being emitted by these ions, can in fact, and they actually do interact. And so one example of this is what's called an ultraperipheral collision, where you get a photon from one lead nucleus that interacts either with the nucleus itself or interacts with a photon from the other nucleus. And so the LHC actually turns from proton and a lead collider into what's called a photon collider. So you're having a massive interaction between two really, really energetic photons. And so there's a bunch of different things you can do with this. One kind of really interesting thing is that because you're actually doing two one interesting thing is that actually because of these because of how the way these collisions happen, you can actually do kind of double slit interferometry in a very basic sense. And you could do a lot of kind of basic tests of quantum mechanics this way. Or another one that I kind of find very interesting is the search for magnetic monopoles. So one theory about how these magnetic monopoles may be produced is by collisions of two photons, which we can actually do experimentally in this case. And So what we can do is actually this the magnetic monopoles can be produced, and so you can actually search for these kinds of magnetic poles within some sort of model. And so this is one example from the Atlas collaboration that does this measurement. They didn't find it, so we're still looking for it. But this is just one example of what we can do. What's also interesting is that if you think about what creates a magnetic field is the flow of charge, right? And you've got a lot of charge in these lead beams, and they're moving quite quickly, and so the magnetic field is incredibly intense. So the only other kind of naturally occurring phenomenon in nature that produces very large magnetic fields is what's called a magnetar, which is a neutron star with a large magnetic field. There, the B field is around 10 to the 11 Tesla. And actually, the magnetic fields that we create in these UPCs, these ultra-peripheral collisions, is actually 5 orders of magnitude higher than that, at 10 to the 16 Tesla. So we are very much, sort of beating out a lot of these kind of large, very rare, kind of extraordinary astrophysical phenomena in terms of the kind of conditions we can produce. Another one is actually neutron stars. So there's actually some theories that neutron stars in their core could have some level of QGP. These neutron stars are so dense, and the pressure is just so high that actually a lot of this pressure can produce maybe some kind of QGP. And there's also some theories that actually the kind of particles inside neutron stars may not just be neutrons, maybe some protons, but actually some kind of more exotic particles that we can actually produce at the LHC. So one example of this is what's called a hyperon. A hyperon is just kind of sounds cool, but really what a hyperon is just kind of a particle the same way as a proton or a neutron is, but it contains one strange quark. So for example, this omega minus, this particle is what's called an SSS bound state. It's just 3 strange quarks put together. And so we can ask, well, could they actually be present inside neutron star cores? The problem is that we don't actually understand how hyperons and nucleons like protons and neutrons interact. Right? And essentially the question is, what's their interaction potential, right? In the same way that we can think about, well, we understand how a hydrogen atom works because we know what the interaction potential is between the proton inside and the electron. We also need to understand what the actual interaction potential is between hyperons and nucleons in order to sort of understand, well, could they actually be inside neutron star cores? So one way to actually do this is with what's called the correlation function method. So you can actually measure the interaction potential as a function of whatever you want with a particle collider like this. And so what you can do is actually, this is one example of the correlation function between the C baryon, which I believe is UDS, with a proton, and the same with a proton and the omega minus baryon. And so what we can actually see is that as for the correlation function, if the interactions is repulsive, which is in this red dotted, that means that the correlation function should be less than 1 between 0 and 1. It should sit between 0 and 1. And if it's attractive, the correlation function should be kind of this this kind of green curve here, where it's greater than 1. And so if you clearly just compare, this picture here to these kinds of to these measured correlation functions, you can tell that clearly it is attractive, repulsive, which means that they could actually be inside neutron stars. There is a bunch of stuff that I've actually skipped. So for one example is quarkonia. So the quarkonia is essentially like an atom, but just in the QCD space. So in the same way that an atom is a positively charged thing and a negatively charged thing that's in a bound state, you can also have quarkonia, where one thing is one color, a red maybe, or an anti-red, and you can get like a bound state that way. So that's what's called quarkonia. And so there's a lot of things you can do with those kinds of states. Also, one thing that I also haven't really talked about at all is actually how you actually do any of these measurements. What I find really interesting about this field is that it's really up to your creativity. QCD is very complicated, so you really want to kind of construct things and measure things that that will tell you what you want to learn about QCD. And so a lot of these things come down to the kind of technologies that you use into building an actual particle detector that can do all the measurements that you want it to. Of course, we've gotten actually quite good at building particle detectors, especially for things like ATLAS and CMS and all of these kind of collider experiments. In particular for a collider detector that is meant for heavy ions, there's some common challenges with more generic particle physics detectors, but also kind of some unique challenges as well. And so the ways that we kind of approach those problems is also very interesting. There's also what's called the QCD phase diagram. So you've probably seen this kind of diagram, phase diagram of the pressure and the temperature for, say, water, for example. And you can do this for generic QCD matter. And here, this is one example of what that might look like. This is a function of the baryon density, so just how much pressure there is versus the temperature. And so actually the LHC only really observes kind of like this upper area here at the very high temperatures and very low density. And so there's actually so much more that we really haven't covered with a collider like this. And so for example, there's RIC, which is another collider based in New York on Long Island. So that's the relativistic heavy ion collider that's there. the SPS, which is also another facility at CERN, which is a fixed target facility at CERN that you can, and the SPS really explores this area of the phase diagram, and of course a couple more. And so you can see some different kind of phases. You have the QGP phase, which we've been talking about, the hadron phase, which is sort of our everyday lives, and the nuclei down here at very low density and very low temperature, but also kind of neutron stars and very exotic other things like Collider superconductors that you can also see as well. So I should also mention that their fixed target experiments are also really important to this field. So in the particle physics sense, fixed target experiments are not so useful because typically in particle physics, the thing you really want is energy. You want to collide these things as high energy as possible. And typically that means that in a circuit collider, you get larger energies than you would in a fixed target where you're smashing a beam of some particles into a target material of some other material, of some other particles. In QCD studies and in heavy ion studies, that is totally wrong. Actually, the fixed target experiments occupy a very important part of what we want to do because actually the energy is not actually so relevant for us. And so actually in terms of the density, so for example, the SPS program are really useful in kind of understanding different phases of the QCD matter that we can see. And so fixed target experiments are and still remain to be a very large part of our understanding of how these QCD matter forms and interacts. And of course, I've skipped a lot of other things as well. Sorry. Looks like it's not. Whoa. Okay. Sorry. Okay. I think that's it. Yeah. So this is a campus lecture, so I would be remiss not to talk about kind of the opportunities here at Berkeley, in case you're interested. The one person that is working on heavy ion physics here at Berkeley is Professor Barbara Yatzak, who's actually also my PI. And there's also a large contingent of people that work in heavy ion physics at Berkeley Lab as well. So for example, this is the relativistic nuclear collisions group that exists within the nuclear science division at LBL. And so there's a lot of people working on not only heavy ion physics, but also related fields there. And so that experiment, that division works really in every area of every aspect of heavy ion physics in a variety of experiments. So for example, I work on the LHC experiment at the Large Hadron Collider, but there's also a lot of other things that you can do, a lot of other places where these kinds of studies are being done. For example, the STAR, Phoenix, and S-Phoenix detectors at the relativistic heavy ion collider, which is currently running. And also what's kind of exciting for us is a future detector on US soil, which is the nearest one, called the EIC, the Electron Ion Collider, and the EPIC detector at that collider. There's also a wide range of people who work on generic kind of nuclear physics in general at Berkeley. So for example, Lattice QCD, one of our, I guess, relatively new faculty, or Raul Briseño, he works on Lattice QCD, which is a more theoretical side of what we've been talking about today, as well as people that work on neutrinos, like Professor Kolomensky and Professor Rebigan, just to name a few, and also things like dark matter as well. And so at Berkeley, we do kind of everything, right? We do not only data analysis to actually understand all of these phenomena itself, but we can also do detector construction to actually build these particle detectors and see what we can do. Also related to computing, right? In the kind of traditional particle physics sense, there's a lot of data to be analyzed. Can't just do that on a laptop. So there's a lot of kind of computing resources that we need to do all of our data analysis, and also EIC as well. I guess this was supposed to play, but okay, it's not playing. Never mind. All right, anyway. Oh, it is running. What? Okay, never mind. I guess I really tried with that animation, but whatever. So what's in the future? So heavy ion physics is essentially just the field of investigating the interaction between quarks and gluons at high temperatures. There's still a lot of mysteries to uncover. This is a very complicated field, kind of really interesting. There's lots of parallels to other kinds of things. QGP is just one example of what's called a very strongly coupled system. And this is where a lot of really interesting research is being done, not only in nuclear physics, but also other systems like high temperature superconductors and cold Fermi atom systems, just to name a few of kind of different strongly coupled systems as well. From the detector side, of course, there is the large high luminosity LHC, which you may have heard before. That begins in 2030. So we should have a lot more statistics for a lot of kind of rare phenomena, and essentially every detector at the LHC is being upgraded for the high lumi LHC. So this is going to be a really interesting time in the next 10 to 20 years to see what new things we can discover. I think that's I've kind of come to the end of my presentation. So thank you much. Thanks a lot for listening, and I'll take any questions. Sure.
So UPC
Mhm.
to create those.
How close? I think 10 to the 16 Tesla is how close? I know they're like on the scale of femtometers. So that's kind of the length scale of like a proton-ish. How far exactly? Good point. Um, Not totally sure. Totally sure. But these are like relatively rare. UPCs are relatively rare. Because again, these like the beams are not so tight. Right? These lead ions themselves are kind of well spaced apart. So the likelihood of a UPC collision is like it's not like a very common phenomenon, but it does happen, relatively common enough to do measurements like this, for example, of like a magnetic monopole search. Yeah.
And if like last.
Yeah, I mean, it depends really on the kind of hyperon you're looking at. So typically we think about, lifetimes on the level of, maybe a few Fermi per C. So typically, or actually maybe a lot longer than that. So for one example, like the omega minus, the C minus, probably on the level of a few millimeters, maybe a few millimeters per C. So these things will decay for, these will come out, they'll come out for about, a couple millimeters, maybe that much, and then they'll decay. So that's one example. The lambda, for example, that's another hyperon. I think that is UDS actually. So maybe the omega like C minus is not UDS. Anyway, the lambda is another example of a hyperon that is on the level of like centimeters. So there's like a large range, and so actually figuring out how to, how much or how to actually theoretically calculate these kinds of lifetimes and stuff is also a really interesting part of nuclear physics that didn't really get into, but also something there. Yeah. Yeah, that's a really good question. So it turns out it's really more about practicality than anything else, right? Because you have to think about lead itself is not so hard to make, right? But what you have to be careful of is that you want to make lead, and you also need to strip off all of the electrons onto it because you want just the lead ion, right? You just want the nucleus. And so it really depends on the kind of facilities you have and what kind of capabilities you have. So in terms of the LHC, there was actually a really interesting article a few days ago that I read on how they actually do this. They essentially just take these lead ions. There's like essentially just these are you just take like a little kind of beaker, and there's like a little like lead shavings, like really, really pure lead shaving. So they stick this into an oven, essentially just boil off the lead. So you get these kind of lead atoms that are kind of floating around. You can bombard them with electrons to strip off all the electrons, and then you kind of circulate them, get them up to high energies and so on. But depending on the kind of ions that you can produce and which ones you can strip off and get up to a high enough energy to put them into your collider, that's really the question. So for example, I mentioned RHIC, the relativistic heavy ion collider. There they do not collide lead, they collide gold. So it really kind of comes down to more the practicalities of what you have on hand to strip off. Yeah. Yeah. Yeah, because so we do want at least like relatively heavy. So it kind of comes down to really also history. So at the point that these things were being proposed, we weren't really sure that we could produce QGP. Right? There were some questions about like, well, is the energy density large enough to actually produce the QGP? So in that sense, you want to get it as heavy as you can, right? You want to because if you pick something like medium or light, the question there might not be, well, okay, we didn't create QGP, but maybe the question is like, oh, we didn't actually get enough energy in there to produce a QGP. So from a practical aspect, if you just want to discover QGP, you want to make it as easy as possible on you. So you basically just get out, how heavy you can get, however much you can get in terms of the mass. Since then, so now that we've kind of established that lead is clearly, lead and gold clearly you can use to create QGP, there's been a lot of questions about, okay, now what is the limit? So we know that in protons, probably no QGP. In lead and gold, probably, very likely QGP. Now, where along that continuum do we go from not QGP to QGP? And so there's been a lot of efforts both at the LHC and at RHIC to use kind of different kinds of ions and see like at what point do we start to see these kind of collective phenomena and we can actually start to see these QGP signatures. There was actually a really, really interesting result that was shown by the STAR experiment at RHIC, actually just a few weeks ago, where they collided oxygen on oxygen. So oxygen is like not too heavy, right? That's like 8. right? So in principle, you might think, okay, that's like a relatively small system, but there's actually some hints there that there are evidence of jet quenching or quenching of ions or of single hadrons in oxygen-oxygen collisions. And so that kind of, all of these kinds of things are now, we're sort of in this area where, okay, now we can actually start searching along this continuum. Our technology's improved in terms of what kind of ions we can produce. So a lot of these kinds of things are kind of, coming to a head at this point. And so, LHC is actually also going to collide oxygen-oxygen this year at a higher energy than at RIC. So it'll be really interesting at that point to kind of compare the results that we get from RIC in OO collisions versus that the LHC will also with OO and see what kind of different phenomena we can uncover there. So yeah, we're sort of in that kind of the middle area where we're trying to figure out, okay, where exactly is this stuff happening? Because again, like this, this kind of question about, okay, we talked about QGP and proton collisions, right? So clearly now, like the kind of major part of the field that what we want to understand is less about like, are we actually producing QGP and like what is now the limits of producing QGP? And in terms of that, being able to collide different ions is very useful. Yeah. Yeah. So typically the way that you want to do it, so lead, the reason why so there's a very particular lead ion that we use called lead 208. It's what's called a doubly magic number. So if you know anything about nuclear stability, you know about these things called like magic numbers. It's actually like the full shells that you get in the spectra. And so lead 208 we use because it's one, incredibly stable, and two, it's very circular. So these kind of ideas about centrality, that where we kind of approximate our nuclei circles, is quite close. In terms of other ions like oxygen, these things are very non-circular actually. So the oxygen is actually kind of like bowling pin shaped. So there's a kind of lots of funny papers that kind of reference the fact that it looks like a bowling pin. And so that kind of can complicate your understanding. In terms of the isotopes that you can use, I think primarily they try to fix the number of isotopes, the level of the particular isotope that you use. For oxygen, there are probably a couple of different ones. But probably during the acceleration process, there are ways to get that out, because typically what is typically the kind of relevant quantity for a collider is what's called the Z/A ratio, the ratio of its charge to its mass. So of course, different isotopes have different mass because they have different numbers of neutrons, right? And so that's one way to kind of even if you're kind of initial sample of whatever thing you have is maybe a little impure, you can actually get rid of a lot of those impurities during the kind of production of those kinds of those ions. Yeah. So I think at the LHC it's oxygen 16 is the target. I don't know why it's 16 though. Maybe for practical reasons. Yeah. Yeah, very good. Yeah, that's a really good question. How do you determine centrality, right? Because you can actually look at a lead ion and be like, okay, I'm going to watch it happen and see these kinds of overlaps occur. That's really tough. So there are a couple of different ways. Number one is you can sort of rely on the fact that, right, when we talked about centrality, we said, well, if you have more central collisions, you see more particles produced on average. Right? So one way to kind of estimate the centrality is to think about, well, let me just measure the total number of particles I measure in the collision and let that be my measure of centrality. So for example, here where we looked at this kind of strangeness enhancement, you'll notice it's like dn charge per d eta. That's a measure of essentially the charge particle, the charge particle density. So that's the number of you're just measuring the total number of particles. So you go from sort of very few particles produced, sort of large numbers of particles produced, going from less than 10 to like over 1,000. That's one way to estimate it. Another way is to actually use a particular kind of a detector. So for typically, one way is to actually measure what's called the spectators. So the spectator ions here. So, in a more central collision, you should have very few spectators, and in a more peripheral collision, you have more of the lead nucleus that doesn't participate in the direction. So the spectators should come out kind of less or more intact, right? You should see more spectators. And so actually these lead ions, they don't get totally kind of broken up, but you get kind of a fragment of the ion that comes out of the collision as a spectator. And so typically what you can use is kind of put a detector kind of at the forward and backward regions, like very far out, very close to the beam line. You can actually measure these things. And this is what we call a kind of a forward detector way of measuring centrality. That's another way of doing it. This is a really big theme kind of in the field also, is to like figure out what are different ways to estimate the centrality and like whether those ways are all equivalent. Because this kind of rough picture is okay, but once you start to kind of get more quantitative and you really want to make like very precise comparisons between two different measurements, say that maybe use two different measures of centrality, then you really have to question like, okay, are we actually, are you and I, when we talk about two different ways of measuring centrality, are we talking about the same thing? So this is kind of a really interesting part of centrality. That's it. Yeah, but that's a really good question. It's a really good question. Okay, well, if there are no other questions, I guess we can stop here. It is 4:05, so yeah. Yeah, thank you.